All right, welcome to This Explainer. Today, we are going to dive into the hidden, literally mind-bending geometry required to safely propel passenger trains at over 250 kilometers per hour. You know, when you think of high-speed rail, you probably picture those sleek aerodynamic bullet trains. But here's the thing. The real secret to their incredible speed isn't actually in the train itself. It's buried right there in the dirt, the gravel, and the mathematics of the track. I mean, we're talking about guiding a rigid 400-ton piece of metal across the Earth's surface at the speed of a low-flying aircraft. To actually make that happen, the physical ground has to be manipulated with absolute, uncompromising perfection.
So, to wrap our heads around this, here's our agenda for today. First, we'll look at the high-speed geometry problem. Then, we'll master the X and Y axes in the horizontal plane. After that, we'll conquer the Z axis in the vertical plane. And finally, we'll look at designing for comfort and safety.
Right, let's jump straight into Section 1, the high-speed geometry problem.
Now, you've probably wondered at some point, why do we spend billions of dollars building entirely new dedicated passenger lines instead of, just upgrading the tracks we already have? It's a completely valid question. After all, a track is just two steel rails, right? Why can't a faster train just drive on the old rails, maybe with a few reinforced ties or some upgraded signals? Well,
the core issue here is a fundamental geometry problem. Physics dictates that you literally can't meet the track banking requirements for two vastly different trains at the exact same time. Let's look at the numbers. Say you have a standard 4,000-meter curve. An 80-kilometer-per-hour heavy goods train needs only 19 millimeters of track elevation to safely round that bend. But a 300-kilometer-per-hour high-speed passenger train, that demands a massive 265 millimeters of elevation on that exact same curve. You simply can't provide an in-between value without causing a dangerous, destabilizing imbalance for both of them. The freight train would grind heavily against the inner rail, and the bullet train would threaten to just fly right off the outer rail. They physically can't share the same geometric space.
Okay, moving on to Section 2, let's look at the horizontal plane and mastering the X and Y axes.
Let's see how the horizontal geometry has to drastically change at these extreme velocities. When a train is moving sideways through a curve at incredible speed, centrifugal forces desperately want to push the entire train and everyone inside it outward against the wall. Think about being in a car, right? Taking a sharp highway exit just a little too fast. You feel your body instantly pushed against the door. Now take that force and multiply it by 10 for a bullet train. That massive outward push is exactly why we see sweeping, massively wide track layouts. The track geometry itself actually has to physically fight the immense forces of high speed.
To combat that intense lateral acceleration, engineers use a highly specialized technique called cant, or superelevation. It's essentially like a steeply banked corner on an auto racetrack. By raising the outer rail precisely above the inner rail, the track gently tips the entire train inward. What this does is use the Earth's gravity to perfectly cancel out that outward centrifugal force, redirecting the energy safely down into the track bed rather than out into the surrounding landscape. It's quite brilliant, really.
but here's the catch. You have to find the perfect balance for a specific, predetermined speed. Because if you get the math wrong, your passengers are going to have a really miserable time. If the train moves too slowly for how steep the bank is, you get what's called cant excess. Passengers actually feel pulled inward, like they're sliding toward the aisle. But if the train moves too fast, you get cant deficiency, and passengers are violently thrown outward against the window. In either scenario, drinks spill, nausea sets in, and that whole illusion of a smooth, premium ride is totally shattered. Neither is an option for world-class high-speed rail.
Because of these immense physical forces, strict mathematical limits are placed on this system. For dedicated passenger lines, the maximum track banking is typically capped at somewhere between 160 and 200 millimeters. At exactly 180 millimeters of cant, research shows passengers still feel perfectly comfortable, even if the train happens to come to a complete, unexpected stop on the curve. But track width changes the whole equation. Global standard gauge is 1435 millimeters wide. Over in India, though, the broad gauge network is a wider 1673 millimeters. Because of this wider stance, the proposed cant deficiency limit for Indian broad gauge high-speed tracks is strictly capped at just 100 millimeters. It's this exact, rigorous intolerance for error that forces engineers to build completely dedicated lines.
So to avoid ever hitting those uncomfortable tipping limits while zooming along at 350 kilometers per hour, you have to flatten the curves out. And I mean really flatten them out. For those Indian broad-gauge high-speed corridors, they're proposing a staggering minimum horizontal curve radius of 5,000 meters. Yes, 5 kilometers. To put that into perspective for you, a curve that massive means that if you're a passenger looking out the front window, the track barely looks like it's turning at all. It's just this gentle, sweeping arc that requires an enormous amount of land just to change the train's direction by a couple of degrees.
All right, let's pivot to Section 3, the vertical plane and conquering the z-axis. So, building perfectly flat lines across a chaotic natural landscape? Basically impossible, unless you want to spend trillions on endless tunnels and viaducts. Trains have to deal with hills and valleys, what the industry calls gradients. Now, pushing a high-speed train up a steep gradient demands a massive amount of kinetic energy, pulling huge loads from the electrical grid. And going down the other side? Those descending gradients drastically increase your required braking distances, which is a massive safety factor. Now, general technical specifications allow gradients up to 3.5%, but countries like France and Germany will sometimes push it to 4.0%. Why? Well, they use highly specialized, dedicated EMUs, electric multiple units. These have motors distributed throughout the entire train, giving them the sheer horsepower needed to climb steeper terrain without bleeding off their speed. But if you want to accommodate mixed traffic, those gradients have to be carefully capped. For instance, the design for Indian high-speed corridors proposes a ruling gradient of 1 in 150. Why such a gentle slope compared to Europe? Because this specific gradient allows existing, much heavier conventional passenger trains, like the Rajdhani or Shatabdi Expresses, to actually share the high-speed line if absolutely necessary. It ensures their heavy locomotives won't just stall out halfway up a hill.
Of course, climbing the hill is really only half the battle. Once you reach the top of that gradient, you can't just have a sharp corner. Imagine hitting a sharp peak at 300 kilometers per hour. You'd launch right into the air. Instead, engineers construct what's called a vertical curve. This is a precisely calculated mathematical arc that gently bridges the upward slope back to flat ground, or smoothly into a downward slope. It completely prevents the passengers from experiencing that violent, stomach-dropping vertical acceleration. You know, that roller coaster feeling of weightlessness? Fun at a theme park, sure, but absolutely unacceptable when you're just trying to drink a hot coffee on your morning commute.
And watch how rapidly these engineering requirements scale up as the speed increases. Because kinetic energy scales with the square of velocity, the math gets exponential really quickly. At 200 kilometers per hour, the absolute minimum vertical curve radius is a pretty manageable 6,400 meters. But as soon as that target speed hits 350 kilometers per hour, that minimum radius required just to keep the train safely glued to the track jumps to a massive 19,600 meters.
But honestly, bare minimums just do not cut it when we're talking about optimal passenger comfort and minimizing long-term structural wear and tear on the track. The actual recommended vertical curve radius for a train traveling at 350 kilometers per hour is a mind-boggling 51,800 meters. Let that sink in for a second. That is a geometric arc longer than a full marathon. Just wrapping your head around the sheer volume of earthwork, leveling, and structural engineering required to carve an arc that massive into the real world, it's just astonishing.
Okay, moving to our final segment, Section 4, Designing for Comfort and Safety.
By strictly enforcing these massive 50-kilometer-long vertical curve radii, engineers are basically ensuring one critical metric. Vertical acceleration forces must never exceed 0.3 to 0.45 meters per second squared. Like we talked about, this is what keeps your coffee in its cup and your stomach totally settled. But far more importantly, it prevents a truly terrifying physics scenario known as wheel offloading. If a train hits the crest of a hill way too fast on a tight curve, that massive upward momentum actually fights against gravity. The wheels could quite literally lift right up off the track. Even a microscopic separation creates violently unfavorable dynamic forces upon landing, which leads to an instant catastrophic derailment. The sheer geometry of the track prevents this from ever even being a possibility.
So, those highly aerodynamic vehicles, they are undeniably the stars of the show. With their sleek noses and ultra-modern interiors, they absolutely capture our collective imagination. But the crucial takeaway from this explainer is that those machines are entirely dependent on the incredibly precise, almost invisible math mapped out over hundreds of kilometers of dirt, concrete, and gravel. It's this flawlessly calculated foundation of curves and gradients that allows them to safely glide across the landscape. Which kind of leaves us with an awe-inspiring question about the future of travel. Knowing that these incredible machines require dedicated tracks with 5-kilometer horizontal sweeps and 50-kilometer vertical arcs, just imagine the sheer unprecedented scale of civil engineering required to blast through mountains and bridge massive valleys, all to conquer the Earth's topography. Thanks for joining me on this explainer today.